Hello, everyone. How are you? This is so exciting. This is actually my very first YouTube live I have ever done. So I'm excited. Thanks for joining me. And I guess I've always wanted to do this. I post videos of me teaching calculus, but you know what? Doing a YouTube live is something I've always wanted to do because it'll allow me to work on the problems with you, and you can comment and you can kind of be there right with me. So to follow along with this video and the 7 problems I'm going to do, actually in the description, I have put a link where you can actually download a free PDF of the problems that I'm going to be doing along with you. Again, I'm so excited. This is my first YouTube live and hopefully first among many. So again, thanks for joining me. And because it is my first one, just have some grace on me. I'm still like figuring out the things, the software, the things that we do to do the live. So again, thanks for having some patience with me. And the best part is that there's comments. So if I make any mistakes, I'm looking to you guys to point out my mistakes and, help me out so I can get those fixed for everybody. So yeah. Oh my gosh, I already have a comment. Hey Cam, thanks for joining. I know I'm excited too. Thank you. And math on a Sunday morning. I would love to hear, Cam, where you're joining from. But yeah, happy to start your day with some calculus. And again, for anybody joining in the link, I'm going to have the link to the free PDF so that you can follow along with me. And today I'm really excited to do, I've chosen 7 practice problems. And these 7 practice problems are actually all about derivatives. So there's lots of good practice here. I picked some 7 problems that will really help you. Home with coffee. Okay. And where is that home, Cam? Is it in the United States, or where are you? Would love to hear. And oh, nice. I love your picture with your guitar. It looks like you play some music. I'll have to check that out. But great to see you have a cup of coffee and you're ready for some calculus. Love to see that. Chicago suburbs. Awesome. Well, thank you for joining us. And like I said, click that PDF below and you'll be able to follow along. So let's get to it. Let's get right to the calculus. And again, thank you so much, everyone, for joining me on my very first YouTube live. It is very exciting. All right. So, like I said, open up that PDF, print it out if you're able to, or if you have a tablet, you can follow right along with me. And let's get headed to the first problem. So the first problem says to find the derivative of f of x equals 1 over x squared minus 5 over x cubed. And the reason I started off with this first one is because it is a common one that students actually take an approach that I would never recommend. Okay. And the approach that I always see is that students see quotients. So they think, oh, I'm going to use the quotient rule because I see these fractions, these quotients. So the first thing I'm going to write over here is the quotient rule. I would not do. Okay, let's go. Okay, so I'm going to write over here quotient rule, and you know what, with a big X. I do not recommend doing quotient rule for this problem, even though you see quotients, probably not the most effective way to do this problem. What I would do instead is I would rewrite this problem first. Do a rewrite, and then taking the derivative is a whole lot easier. And the way that I would rewrite this problem is just rewrite it without fractions. So 1 over x squared, you can actually rewrite as x to the negative second, and it means the same exact thing. And rewriting it that way is going to make taking the derivative a whole lot easier. Highly recommend this. Don't do quotient rule. Later in this live stream, we will be using quotient rule. So trust me, we'll get plenty of practice with quotient rule. Just don't do it yet. And then minus 5 x to the third, we can rewrite as x to the negative third because that x to the third was in the denominator. Okay, rewriting it like this way, it's going to be so much easier to take the derivative because now I can use what's called the power rule to take the derivative. So next would be using the power rule. And let me go ahead and write out that rule in case it's new to you, or if you need a good refresher, that's always helpful. So the power rule says if I want to take the derivative with respect to x of, let's say, x to the power of n, that derivative is going to be, you bring the n out in front as like a constant multiple, and then raise x to the power of n minus 1. And again, that is called the power rule. And because we've written both of these terms as a power, we can now incorporate the power rule, and again, way easier than that quotient rule. Notation, because we are finding the derivative, make sure to say f prime of x. And now power rule, the exponent of negative 2, I am going to bring that out in front as a constant multiple, and then x to the power of, remember you want to subtract 1 from the exponent, so be careful with those negatives. Make sure to go minus 1, so in the more negative direction. So negative 2 minus 1 is going to give us negative 3. And then I have this negative 5 out there already as a coefficient. So when you bring the negative 3 in front, you're going to want to multiply those two numbers together, and then again subtract 1 from the exponent. So negative 3 minus 1 would give us negative 4. And okay, that's fine. You can leave it like this, but I think it'd look a lot nicer if we cleaned that up. So let's rewrite this as f prime of x equals negative 2x to the negative third. We can rewrite that x to the third back in the denominator and give it a positive exponent, but leave that negative 2 in the numerator because negative 2 does not have a negative exponent. And I already see a little mistake I made. I forgot when I bring that exponent down below, I do need to make it positive. So let's try that again. All right, negative 2 over x cubed. And then I would multiply the negative 5 with the negative 3 to get a positive 15. And again, let's bring that x to the fourth into the denominator. And there we have it. That's a nice cleaned up answer, cleaned up because it doesn't have any negative exponents. I always think it looks nicer that way. And that's it. That's the derivative. That's first question. Find the derivative of f of x. Again, I wouldn't recommend using that quotient rule. I would recommend rewriting it because when you rewrite it, you're able to use that power rule. All right, first question on my YouTube live ever is done. So thanks for doing that with me. And again, please have some patience on me in case I make any mistakes being my first YouTube live, and put those comments in there if you catch any mistakes. That'll really help me out. Oh, great question. All right, thanks, Cam. So, would kids taking AP Calculus? So, in the United States, we've got, and maybe around the world, I don't know. You guys will have to tell me, but we've got this advanced placement calculus class in some high schools. And would they be expected to simplify the negative exponents? Do you know? And that is a fantastic question. Thanks for giving that question. So, I would say this. A question like this, I'll be honest, is most likely going to be assessed on the multiple choice portion of the AP exam. That's why when I teach this problem, I always like to rewrite it with positive exponents, because on the multiple choice, most likely going to be those positive exponents. However, if this question or a question similar to this would be on an FRQ, which is a free response question, you would not be expected to simplify those exponents because it is an equivalent form. So yeah, thanks for that question. I would say, to me, it depends if it's multiple choice or free response. But I thought I would show those positive exponents because, again, this question would most likely be on a multiple choice question. Thanks, Cam. Keep those questions coming. Yeah, absolutely. You're very welcome. Okay, let's move it right on down. Okay, question number 2. Find the x value. Okay, a little bit different, where the slope of f of x is equal to 6. The slope of f of x, the slope of a function, actually means the same thing as the derivative. So as soon as I read that sentence, I'm thinking, okay, I need to find where is f prime of x, which is the slope of f of x, and where is that equal to 6? Okay, we need to find the x value where that happens. So as you can see what I wrote out in blue, it first requires that we take the derivative. We find f prime of x. And I'll tell you again, I'm guessing this is a common one that students would maybe think differently than me. Because why? Because they see this quotient. Anytime my students see, oh, it's a quotient, I have to use the quotient rule. And I'm thinking, Yes, sometimes, but in this case, it would be so much easier if you actually did not use the quotient rule. And again, if we did a rewrite instead. So I'm going to say on this one, you know what, everybody? I am not going quotient rule on this one. I am going with a rewrite. And the reason I'm doing this is because the denominator is just 6. It's just a constant. So I think when you're dividing just by a constant, I would say let's simplify this first. So what I'm going to do is I'm going to take each term, divide it by that constant of 6. So let me show you what that would look like. So I think I've copied that down correctly. And then from there, I can even simplify further. So 2 divided by 6 would give me 1/3 x cubed. And then the 3 divided by 6 would give me the 1/2 x squared. Okay, and the reason I want to rewrite it like that is because look, now you don't have to do the quotient rule. Guess what we use again, just like last time? That power rule. So next I'm going to use the power rule to take the derivative. So here we have f prime of x. And again, remember that power rule is when you want to take the derivative with respect to x of x to the power of n. That would be n times x to the power of n minus 1. All right, so now that I have the first term written as 1/3 x cubed, what I want to do is I want to first, well, I first have that constant of 1/3 out front. So that 3, I'm going to multiply the 3 down in front and then subtract 1 from the exponent. So if my exponent is 3 and I subtract 1, I would have 2. And then minus the coefficient of 1/2, bring down the exponent of 2, and then again, subtract 1. So 2 minus 1 is 1. You don't have to write that, but I'm going to write it because in the next step, I'll go ahead and simplify those. So let's see, simplifying my derivative is going to be 1/3 times 3. That's really nice. Those 3's would cancel, and I'd just be left with an x squared. And then I would have minus, same thing here, 1/2 times 2 is just 1, and then x to the first is just x. So I've kind of done my first step, and that is to find f prime of x, and that is x squared minus x. And then remember, I wrote up here above that really when I want to find where the slope of f of x is equal to 6, it's really where that derivative that I just found, x squared minus x, is equal to 6. So I sense an algebraic equation coming up. And again, for those of you joining us, I just wanted to remind you that down in the description, you can find a link to where you can actually get these problems that I am doing right now and follow along with me. So what I'm going to do is I'm going to set that derivative equal to 6, which is what I kind of identified as I read the original question, what I need to do. And here we do. We have an algebraic equation. We actually have a quadratic equation. And so for this, I'm going to subtract the 6 over and solve this quadratic by factoring. And so let's see, the factors that would multiply to x squared minus x minus 6, I believe is x minus 3 times x plus 2. As long as I've done that correctly there. Again, would love to hear comments from you if I make any mistakes, because it's my first YouTube live here. If I make any mistakes, I'm counting on you to point them out. Setting each of those factors equal to 0, I would have x minus 3 equals 0 and x plus 2 equals 0, therefore getting solutions of positive 3 and negative 2. All right, and I think I've answered the question. Let me just make sure. Find the x value. You know what this problem should say? Value or value. It's because it sounds like I have 2 of them, where the slope of f of x is equal to 6. And that's it. We have found, in this case, they happen to be 2 x values. And so what does that mean? That means, and if I would have prepared a little more, I'll do this next time. I could have had this graph all ready to go and graphed for you. And so if you graph this in this case, a cubic, if you graph this cubic equation, well, at the x values of 3 and negative 2, if you were to draw in the tangent line, okay, that tangent line at the x values of 3 and negative 2 would have a slope of 6. So I encourage you to try that, graph that function, graph this f of x function, and find the x values of 3 and negative 2, and think about a little tangent line being drawn and have a slope of 6. I think that's so powerful to see that, to see that graph and see that connection. And when I teach this in class, I always try to do that. I always try to pull up the graph and make that connection, because I think it's really cool, to see that. Okay, I've got a comment over here. Let me see. What you said, Kim, is there ever a case where you would get rid of one? Is there ever a case where you would get rid of one? Oh, get rid of, okay, I was like, get rid of the number one? Sorry, but I'm guessing you mean get rid of one of the solutions. Oh, that's a really good question. You know what, Cam? I'm thinking of, because if you of the X values. Yeah, exactly. Yeah. No, no worries. Yeah, thanks. Thanks for that question. And I would say, if you were to graph the entire function f of x, both of those would be solutions. And I would say the only time I would get rid of one is if they gave you an interval. So if it said, for example, find the x values, maybe the answer is find the x values on something like 0 to 5 where the slope is equal to 6. And that's one thing we would need to then check if we get our answers. Okay, all solutions from 0 to 5. Oh, I'm getting rid of the -2. So yeah, I would say that's when I would only include one of those two x values if they gave you an interval. But as long as we're open to the entire function, I would say, yeah, they're both going to be they're both going to be solutions that we would have. Yeah, absolutely. Yeah, thanks for that question. All right, so that is question number 2, and let's keep it going. Let's keep it going. Keep the comments coming. Again, if you're just tuning in the description below, I have the free PDF of actually this exact document that I'm writing on right now. You'll be able to take a look at and follow right along with me. All right, the moment you've all been waiting for. I've said we are not doing quotient rule on number 2. We are not doing quotient rule on wait, I started with number 2. Let me try again. I teach math and I know how to count. We were not using quotient rule on problem number 1 nor number 2. All right, I'll let you use it on this one. This is definitely one that if you needed to take the derivative of this function, I would say, yeah, quotient rule, totally fine. I would say it's not going to be a rewrite problem. So I've been holding you in suspense to use that quotient rule. And okay, I'll finally let us use it here. So since this is the first problem I'm doing quotient rule with you, let me go ahead and review the quotient rule with you. Rules are something that's very important in calculus, whether it's the power rule, the quotient rule, or even later, we're going to see the product rule. Knowing your rules is definitely something you want to be able to do. So let's review quotient rule. If I am taking the derivative with respect to x of a quotient, and I usually use f of x in this one, but my original problem uses f of x. So let me not use f of x. Let's see. How about g and h? Sure, let's do it. Okay. Let's say I have the quotient of g of x over h of x, and I need to take the derivative. All right. So the derivative would be, so the quotient rule. And a common mistake that students make is they just take the derivative, of the top function, the derivative of the bottom function. I'm like, no, we got to use our quotient rule. We can't do that. So the quotient rule looks like this. We take the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. All right. So there it is, quotient rule. Make sure to use those, make sure to know those rules. And I always encourage people to make flashcards if that helps you. But so far, the two big rules we've done is we've done power rule so far in problems 1 and 2, and then this one, quotient rule. So in our case, if we now want to take the derivative of f of x, so my notation would be f prime of x, think of this x squared minus 9 function then being the g of x over here in my rule, and then this denominator function being h of x. And I can kind of go along then with the rule that I wrote in blue as we take the derivative. So we've got one big fraction. Let me go ahead and kind of get my setup here. All right, the first thing in quotient rule, g prime of x, which means the derivative of the numerator. And because we've been practicing power rule, let's just keep it going. So derivative of x squared minus 9 using power rule would be 2x. And I did not go over this before, but if you're taking the derivative of a constant, so the derivative with respect to derivative with respect to x of a constant will always be 0. And I love when that shows up in a derivative problem because boom, it disappears. The derivative is 0. So g prime of x is going to be 2x. So the derivative of the numerator time, and then we have a minus, and we have minus g of x, which is x squared minus 9, times the derivative of h of x, the derivative of the denominator. So 3 plus x, the derivative of 3, because it's a constant, is just 0, and the derivative of x is 1. So x squared minus 9 times 1. That looks really nice. All right, I think that is it for the numerator. So let me go ahead and erase the rest of that line there. And then in the denominator, we have to take h of x squared. So this is going to be 3 plus x, the quantity, squared. So make sure to use those parentheses for the quantity. Okay, so Cam, back to your question about whether, we have to simplify these things. Again, if this is on an AP exam, for example, and it's on a free response question, you would not be expected to simplify this problem right here. You can just leave it just like that. But again, what I like to do is simplify. It also helps our algebra skills. And if this were a multiple choice question, you would be expected to simplify this. So let's grow our brain here and just practice some problem solving. So f prime of x equals, let's distribute our 2x. So 2x times 3, we've got a 6x there and a plus 2x squared. Again, this is my very first YouTube live. Let me remind you. So if I make any mistakes, get right in those comments and comment because, I'm bound to make mistakes when I'm doing this live. All right. There's no video editing here. So help me out. Okay. Minus. And x squared minus 9 times 1 is just x squared minus 9, but I need to be careful about that negative. So I'm going to distribute the negative into there, and then I would have a minus 9, but distributing the negative in would give me a plus 9. And in the denominator, I've got the 3 plus x squared. So you know what? For right now, I'm just going to leave that as 3 plus x squared. I'll see later if I need to multiply that out, but for right now, I'll just leave it. Okay, let's see. I think we've got some like terms in the numerator we can combine together. How about those x squareds? 2x squared minus 1x squared would give me x squared. And then I've got, those were the only like terms. So I've got a plus 6x and then a plus 9. All right, so you know what? I think I actually am going to multiply out that 3 plus x squared now. I mean, I could do that, or I could factor the numerator. You know what? What do you feel like doing? Do you feel like multiplying it out or factoring? You know what? We did factoring in the last problem. So let's go ahead and multiply this one out. So I would have 3 plus x squared, which is 3 plus x times 3 plus x. And if I multiply this, I would have 9 plus 3x plus 3x plus x squared. And combining those like terms together, let's put the denominator here, x squared plus 6x. Oh, I think I found a mistake and no one pointed it out. I don't know why I did this. I put a 6x squared here in the numerator. Let's go back. But I caught it when I was foiling this out on the bottom. So x squared plus 6x plus 9. And there we have it. Something looks the same. So the numerator and denominator on this one are the same. Well, this makes things easy. X squared plus 6x plus 9 over x squared plus 6x plus 9, 1. Wow. After all that work, can you believe it? F prime of x equals 1. There it is. Wow. Lots of algebra to get a final answer of 1. Interesting. Well, there it is. All right. So find the derivative of that. And again, I saved you the suspense here, but I did let you use the quotient rule on this one. So quotient rule gets us a derivative of 1. Oh, we got a challenge here. Okay. Can you find the derivative of f of x again using a different method from above? Okay. I love this. It makes us really think. I love questions like this where you're given a problem and you do all this work to solve it. It's like, now do it again, just in a different way. But it's really good because it makes you think. So what was it? X squared minus 9 over 3 plus x. Let me write that down again. So f of x equals x squared minus 9 over 3 plus x. Okay, find the derivative again using a different method. And we can't use the quotient rule. And I'm trying to think, otherwise we usually just rewrite it, but there's nothing we can do. I see something. All right. We've got wait, Kay, I'm sorry. I just saw your comment. Let me pull it up. Are there shortcuts to know when that stuff will cancel out? Oh, this might answer my question. I think so. It's coming. Okay. So I just noticed something. X squared minus 9. That right there is what we call a difference of squares when you, and what I mean by that is when you go to factor it. So for example, if I had something like a squared minus b squared, which is what I have right now, I'll show you kind of that format in just a bit. This would factor into a plus b. So in our case, we have x squared minus 9, but if I wanted to write that as a difference of squares, I can write it as x squared minus 3 squared. So then my factors would be x plus 3 and x minus 3. I think I see what's going to happen. What's going to happen here? It's going to be something I can actually simplify and then take the derivative. Okay, maybe I like this method better than the quotient rule in this problem, for example. So this would be x plus 3, x minus 3 is what I would factor that x squared minus 9 to. And then in the denominator, I have 3 plus x, which actually is the same thing as x plus 3, which is that the commutative property, I believe. So here I would have x plus 3 over 3 plus x that I can cancel out. And I have a simplified answer of x minus 3. Okay, yep. I think I'm going to go simplify all the way on this one rather than the quotient rule, because taking the derivative of x minus 3, oh yeah, whole lot easier. I'd take these derivatives all day long. So f prime of x equals, now I can just take the derivative of each term. Derivative of x is 1. Derivative of minus 3 is a constant. And as we discussed in problem number 2, the derivative of a constant is just 0. So I don't need that anymore. And look at that. F prime of x equals 1. Is that what we got up above? Oh yeah, sure did, right there in green. And we used a different method. Okay, I love that. I love that you can use different methods to find the same derivative. And it is very satisfying at the end when you get that same exact answer. Okay. And by the way, I just want to remind anybody that's kind of joining here that down in the description below, I do have a link where you can actually get these exact problems, the PDF of these problems that I'm doing. And if you want to, follow along on your tablet or print it off, or just be able to have these problems later to refer back to them, just want to remind you that I do have that in the description below. And what I do every week is I post videos, and I really do hope to do some more lives later. So if you subscribe to the channel, if you haven't subscribed already, just consider subscribing. That way, as I do more YouTube lives in the future, you'll be notified and follow along with me. And I love, I love hearing from you guys. And for those of you coming in, I would love to hear where you're listening in from. All right. So I think that's it for that problem. Let's keep going here. Oh, where's my cursor? There we go. Okay. So number 4, because first derivative was not enough of a challenge, we're doing a second derivative. Let's kick it up a notch. Let's do a second derivative here. So find the second derivative, f double prime of x of f of x equals x minus x cosine x. Okay, this is good. There's some trig, and there's also a product rule. We've been doing quotient rule, we've been doing power rule, but now we got a product rule. Yeah, Cam, will it be on the weekends? Oh, like the YouTube lives? Yeah, I'm thinking on the weekends that probably best for people. So I'm going to try to do it next weekend as well. Yeah, next weekend, maybe next Saturday. So Cam, check it out. I'm thinking next Saturday, I'll do another one. We'll do some more practice problems next Saturday. Okay, so find the second derivative of f of x. Well, we know to get the second derivative, we got to find the first derivative. So let's start with that first derivative. And we've been taking the derivative of x a couple times already. So derivative of x, 1 minus. Okay, now we have x cosine x. We've got trig in here, and we've also got a product, x cosine x. So what we're going to have to use here is we are going to have to use product rule. And that is because we have x times cosine x. So far, I've reviewed power rule with you. I've reviewed quotient rule with you. It's time to review product rule. You need to know these rules. I know it's annoying reviewing all these rules, but that's how you really succeed in this class. Okay, so power rule. The derivative with respect to x, and I usually use f of x when I show the rule, but f of x is in the problem. So let's not use f of x. Let's use g and h again. Okay, so here we go. We've got the product of g of x times h of x. And I could put the times symbol in there or not. But the derivative is going to be, you take the derivative of the first function, derivative of g of x, times the second function, h of x, and then plus the first function, g of x, times the derivative of the second function. So review your rules. Know those rules. They are very important to be able to do these problems. Okay, so we already took the derivative of x. Let's come over here and I see minus. And you know what? I'm going to do the product rule, but I'm going to put this in parentheses because that negative could mess us up if we don't use those parentheses. So if you think about kind of the form that I set up, x is really now my g of x function. And then cosine of x is like my h of x function in the rule over to the left in green. So if I take the derivative of x cosine x using product rule, first I would need to take the derivative of g of x. Derivative of x, again, is just 1. And then times h of x, which is just times cosine x times h prime of x. So another thing we do need to know is we need to know our trig derivatives. And we got to our first trig derivative of cosine x. So let me just remind you that the derivative with respect to x of cosine x is, this one is. So derivative of cosine x is going to be negative sine x. Okay, there we have it. All right, so let me kind of simplify this, clean it up a bit. 1, let's distribute the negatives. This would be 1 minus cosine x. And then let's see, the next term when I multiply the x times the negative sign would be a negative x sine x, but I want to distribute the negative in. So this is going to be a plus x sine x as the first derivative. Again, this is my first YouTube live. So if I'm making any mistakes, make sure, put them in the comments. I don't want to post because I do want to post this video after. And I don't want to have wrong answers out there. So again, find some mistakes, comment below. Tell me where you're watching from. Okay, so that's the first derivative, but we kicked this one up a notch. We want the second derivative. First derivative, not enough of a challenge. Let's keep it going here. So let's find the second derivative. Okay, so f double prime of x equals. So we run into, the first is 1. So we need to take the derivative of each term. Well, derivative of 1 is just 0. Because again, we talked about that. The derivative of a constant is, derivative of a constant is just 0. Great, Cam. Great to know that I'm not, thanks for having my back here. Check in. All right. So then we have minus cosine x. So cosine x, we already talked about the derivative. I wrote that over to the left. The derivative of cosine is negative sine. So be careful here. We have a minus and then a derivative of cosine, which is another, negative. And then we would have plus, and I see x sine x. Once again, be careful here. It's actually a product. So you would need to use the product rule. And what I wrote over there in green with product rule, think about x as my g of x function in product rule, and think about sine of x as my h of x function in product rule when we go to do this. And the good thing is there's no negative here, so we don't have to worry about forgetting to distribute the negative or something like that. So derivative of g of x, as I start my product rule here, is 1 times h of x, which is sine of x, plus g of x, which is x, times the derivative of sine. Let's add this one over to our sine x, another good rule that you want to make sure know. So then you would have plus x times the derivative of sine is cosine x. Oh, I don't know why I put a parentheses there. Not needed. I think I'm just so used to parentheses all the time. Okay, so let's clean this up a bit. F double prime of x, which is what we wanted to get to. I want to get to the second derivative. Negative of negative sine of x is going to be a positive sine of x, plus 1 times sine of x is just a sine of x. And I'm going to combine these like terms together. So after double prime of x, sine of x plus sine of x, we've got a good old 2 sine of x plus x cosine x. And I think that's it. I won't make you do the third derivative, but ooh, a problem that I really like actually is when I give like sine or cosine. I'm going to have you think about this. I'm not going to tell you the answer. When I give like sine or cosine and I ask you to find like the 54th derivative or something like that, that's a fun problem. Ooh, I think you know what? I'll do that in a future video. I just decided. That's a good one. That's a really good one. All right. So we just did the second derivative of this one. And there it is with some good rules there on the left. Okay, what do we got here? Problem number 5. Here we go. It's problem number 5. If g of x is cosine x over cosine x minus 2, find the x values Cam, this reminds me of your question you asked earlier about, do you include both answers or which answers? And on this one, it does give an interval. It says only look from 0 to 2 pi. So don't look everywhere. So yeah. And we want to find thanks, Scott. Thanks for that comment. We want to find the x values where the derivative equals 0. So that again involves finding the derivative. And again, quotient rule, definitely the way to go on this one. Quotient rule all the way, because it's cosine x over cosine x minus 2. So in the question above, remember I wrote the rule for quotient rule. So if you need to go back and look at that previous problem to check out that quotient rule, okay? So we want to find where g prime of x is equal to 0. So let's find the derivative and then set it equal to 0 and find our solutions on the interval from 0 to 2 pi. Here we go. G prime of x equals some good old quotient rule practice. We take the derivative of the numerator. So derivative of cosine x is negative sine of x. Derivative of the numerator times the denominator minus of the denominator. Derivative of cosine x minus 2 is just negative sine of x, because the derivative of a minus 2 is just 0. Remember, the derivative of a constant is 0. And then all over, this is going to kind of get messy, all over the denominator squared. Okay, that is quotient rule. Okay, let me just check that. Derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. Okay, I think I got it. So I need to solve for where that derivative is equal to 0. But you know what? I think I am going to clean this up a bit, because it might make the solving just a little bit easier next. So let's clean this up. So g prime of x equals, let's distribute the negative sign in. So then I would have negative sine of x cosine x. And then negative sine times negative 2 would be a positive 2 sine x. Be careful of the signs there, that negative times a negative. And then here I would have a minus, and then a cosine x times a negative sine of x. That would be minus a negative sine x cosine x, which I believe would go to plus. And then plus sine x cosine x. Oh, I like this. I think there's going to be some like terms that cancel out in the numerator. I love when that happens. Again, that is just so great to see. It's so satisfying. So negative sine x cosine x and sine x cosine x gone, just like that. Beautiful. So much nicer. So g prime of x equals, we've got 2 sine of x over minus 2 squared. Okay, so we found the derivative. We found g prime of x equals 0. And we want to now find where that is equal to 0. Okay, Cam, let me look at your question first. So Cam, can you cancel the cosines? You know what I wish I could do? I wish I could like click a button and allow Cam to talk right now, because I would love to hear like what cosines you're talking about. Is it, okay, I think I'm reading okay, if I am correctly reading your mind, I think you are talking about the cosines in the original. That's my guess. That's my guess. I don't know if this is right. Did I read your mind correctly? So if you're talking about the cosines here, yes, the ones at the start. Okay, I guessed correctly. So cosines x, you actually can't, and I'm really glad you brought this up, because it is a common thing that I think that I see students do, is they think to cancel out the cosines, and they're like, but why? Like, it's a cosine x in the numerator and a cosine x in the denominator. Why can I not just cancel those out? And I say, okay, let me see if I can be convincing here. To be convincing, let me replace cosine x with like a number. Okay, let's replace it with a number instead of something like cosine x, which is a little bit harder to think about. What if, because I totally get what you're saying. If you can cancel the cosine x's, trust me, it makes taking the derivative a whole lot easier. So what if you could? What if in math you had something like, let's make cosine x, I don't know, 5. 5 over 5 minus 2. Well, we know 5 over 5 minus 2, we know that that is equal to 5 thirds, right? 5 minus 2, it's 3. Now, but if you had incorrectly canceled out the 5s, well, you would have negative 1/2, as you can see, very different than 5 thirds. So I hope that helps for you to see we can actually not cancel the cosines out in the original problem, even though, yes, I agree, would have made taking the derivative so much easier, but we can't do that mathematically. It doesn't work out. So thanks for that question. because we can't. All right, so let's see. Hi, hello. What do we need inflection points for? May I ask? Nice to see you're doing fine. Yes, we do have. So yes, I am in the United States in the Midwest, and we have been having such extreme, winter weather conditions. We actually had school canceled because of a snow day, and then there was a weekend, and then after the weekend there was actually, it was so brutally cold that we actually had a cold day, like school was canceled because the cold was so bad. So um thanks for recognizing that. Yeah, it's been been a little bit blustery and cold, and so much so that they had to cancel school for a couple of days. But yeah, so inflection points. That's a great question. So points of inflection, and I'm glad you brought this up, Jan, because then I can put it in a future video about inflection points and kind of the benefits of them. And I would say, typically we find inflection points when we aren't given a graph. And it's helpful then because then we can determine algebraically where in this case, inflection points would be where the concavity changes. So for example, where a function would change from concave up and then switch to concave down. So right here where my fingers connect, that would be your point of inflection. It also is where the second derivative changes sign, because the second derivative tells you about concavity of the function. So it would tell you where the function changes from concave up to concave down. And it's especially useful, again, where you don't have that graph. And even if we did have a graph, you'd have to just estimate it, which we don't want to do. So when given a function, we're able to use the second derivative to find those inflection points. And the inflection points then help us find where that concavity changes, which is, good to know if we can do that algebraically. Okay, so yeah, if this problem was anything about like where does the second derivative equal 0, and then if I could do that and then find where that second derivative changes signs, that would help me find that inflection point, which is pretty cool. So here it's just where the first derivative equals 0. And even though it doesn't talk about in this problem where the first derivative equals 0, that could tell us something about something called critical points in calculus. But that is neither here nor there. I'm thinking about everything like on my mind right now that I want to say. So I want to find where the derivative equals 0. So let's set that derivative. Oh, my marker's not working here. Okay, come on. Let me go back. There we go. Okay, so I want to find where this derivative equals 0. And you know what? My pen is not working. I wonder if it like ran out of battery or something. Oh, this would be interesting. Let me try to use my finger here. So it's where this derivative is equal to 0. And again, my pen battery went out. So I would be using my finger. It might be a little bit messy. Okay, so where is this derivative equal to 0? Well, think about this. If you were to multiply over the denominator, then notice then we will have okay, thanks, Cam. Yeah, plug it in. Got a minute to charge. Okay, so if I multiply over the denominator, notice it would be where 2 sine of x is equal to 0. And also think about that. If you have, a fraction, where would your fraction? Oh goodness. Okay, let me see if. You know what? That's just a whole lot harder. Let me try to go back here. Okay. I charge it for like a good third equal to 0. And again, you'd have that if you like multiplied over the denominator, or it's where the numerator equals 0. So where 2 sine x is equal to 0, well, dividing both sides by 2, I'd get where sine of x is equal to 0. This is really good trig practice. Okay, where is sine of x equal to 0? In a problem like this, I would like to use the unit circle. So let me show you that real quick in case trig is not your strong suit. Just like a lot of my students, trig is definitely not their strong suit. So let's see if I were to draw the unit circle in which I have these points 1, 0, and 0, -1. All right, sine of x on the unit circle, sine is going to be your y coordinate. So we're looking from 0 to 2 pi. Remember that interval. If they give you an interval, we cannot forget that interval there. So we're looking from 0 to 2 pi, where sine of x equals 0. On the unit circle, sine is the y coordinate. So I see a y coordinate of 0 here and here. And because my interval says 0 to 2 pi, I would want to use radians. So that is going to be where x equals 0 and also pi. And I think that's it. I think we solved for where g prime of x is equal to 0. And in this case, it says find the x value or x values. It looks like we did have 2 x values on this one. All right, so that is it for number 5. All right, so number 5 is that problem. And again, for those of you just coming in the description, I have actually linked these exact questions. So if you ever wanted to click on that link, get the PDF, you can see which problems I did. You can save them for later, try them on your own, or you can follow along with this video as well. And if you're not a subscriber, make sure to click that subscribe button, because I hope to do, again, this is my first YouTube live ever, but I hope to do more in the future. And so if you're a subscriber, you'll be able to see as soon as I do those other YouTube lives. All right, so we're getting down there. I wanted to get to 7 problems today, and this is question number 6. We've got some differentiability and continuity, which is a big thing that comes up in calculus. So if h of x is x to the 3/5, at what x value is h of x differentiable? So differentiable means like derivative. Where does the derivative exist? All right. So in order to do that, I do have to find the derivative. So find the derivative of h of x. So h prime of x. So earlier in this video, we did power rule, and we're going to do that same thing. So if you do power rule, remember, you take the exponent, you bring it out in front as the coefficient. So 3/5 and then x to the power of, and you remember you want to subtract 1 from those exponent. And don't be intimidated by those fractions. You guys can do this. Fractions, we got this. 3/5, and we have to subtract 1. So 3/5 minus 1 would give you negative 2/5. All right, so we want to find where is x of x. So I can talk. H of x differentiable. And you know what? I'm going to rewrite this without a negative exponent. So this would be 3 over 5 x to the positive 2/5, moving that negative exponent to the denominator to make it positive. But again, I want to know, where is h of x differentiable or not differentiable? I'm going to do a little bit of a rewrite again. So h prime of x, I'm actually going to take that x to the 2/5 and write it as a radical. So what if I wrote it in radical form, the 5th root of x squared? Okay, so a fractional exponent, writing it as a radical is just like that. So where does this derivative exist? Or better yet, where does this derivative not exist? Well, this derivative does not exist at any x values that would cause the denominator to equal 0, because that would be undefined. We can't divide by 0. So I would say, where is h of x differentiable? I'm going to write that h of x is differentiable at all x values except x equals 0. Because it looks like that is the only one that would not be okay. Okay, so that means the derivative or the slope of the tangent line would exist at every single x value except x equals 0. So that was the first question. At what x values of h of x differentiable? Okay, next question is, at what x values of h of x continuous but not differentiable? Well, the only x value where this function was not differentiable was x equals 0. So that's really only the only value we really need to think about in this problem is just the 0. What's happening at 0? Is the function continuous at x equals 0? Well, that just, I'm going to rewrite this again in radical form. So x to the 3/5 means the 5th root of x cubed. And so my question is, can I plug in x equals 0 to this function? Would that cause the function to be undefined at all? And no, you can definitely take the 5th root of 0 cubed. That's okay. The function would exist there. The function is continuous. So at what x values of h of x continuous but not differentiable? You know what? There is going to be none. Oh, sorry. No. It is 0. What am I thinking? Continuous, because we could plug in 0. So at what x values of h of x continuous but not differentiable? Oh, almost made the mistake there. Yes. Yeah. I like that, Jan. That's good. Yes. So it would be, all real numbers except x equals 0. So yeah, some different notation ways to write out that answer. I really like that. Yeah. And I also know there's interval notation that you can write it out and, leave out the 0 as well. So different notation wise. And then same function, at what x values is h of x neither continuous nor differentiable? So neither. And this one's going to be the one that's none. neither continuous nor differentiable, because if you look at this original function, again, you can rewrite it as the fifth root of x cubed. This is actually continuous everywhere. And why? Because there's no restrictions on the domain. You can take 0 and cube it and take the fifth root of it. You can take a positive x value, cube it and take it the fifth root of it. Or you could take a negative number and cube it. And you think, but wait, I'm taking a radical. I can't take a radical of a negative number, but it's an odd index. It's a 5. So you can take the fifth root of a negative number. So you know what? This domain of this original function is all real numbers. And do you want a little sketch of it? And again, this is by no means is this a perfect sketch, but x to the 3/5, I think it's going to be, yes, I think it's going to be one that kind of looks like this. I don't know. If I'm wrong, let me know. But I think it's something like this. And you can see that we determined that the function was not differentiable here at x equals 0. And I can see that because if you were to draw in the slope of the tangent line, let me do that, like a little tangent line here, the slope is undefined. And so that's why the function was not differentiable at x equals 0, because it would have a vertical tangent line, and thus the function would not be differentiable there. But as you can see, the function is continuous everywhere. So let me see, Cam. If the function is continuous, can we always assume it's differentiable? Good. I love these questions that make me think. If a function is continuous, is it always differentiable? And you know what? There's a few cases that I can think not. And if there's any more cases that you can think of, let me know. But the first case I can think of is, something that has like a sharp turn. So what I can think of that has a sharp turn often is like an absolute value function. So an absolute value function, as you can see, this function is continuous everywhere, but at this vertex, so at this vertex point right there, the function is actually not differentiable. You can't find the slope of the tangent line there because it makes this drastic change. It makes this drastic change in that slope right there. So that would be an example that is continuous but not differentiable. Something known as like a cusp. So you could have, something like this, but again, that sharp turn. So here's an example of a function that is continuous but is not differentiable. Let's see what else. Yes, and to Jan's point, we had that. Oh yeah, thanks, Cam. So we've got that vertical tangent line at x equals 0. So there's another example that this function was continuous but was not differentiable. So back to your question, if it's continuous, we cannot assume it's differentiable in this problem. And then also something like a sharp turn or a cusp, like that would be continuous but not differentiable everywhere. So vertical tangent line, sharp turn, and the other examples I'm thinking of wouldn't even be continuous. So yeah. So if it's rounded, would it be okay? So something like a parabola, you say. So let's think, if we have a parabola, as we can see, definitely continuous. There's no holes, jumps, vertical asymptotes. And would this be differentiable everywhere? And yes, because there's no sharp turns or there's no vertical tangent lines. And if you think about all these little tangent lines, it makes a nice slow turn, not like that sharp turn that we would have in something like an absolute value. Yes. So in this function, in something like a cubic or a quadratic, like this parabola, it would be continuous and differentiable everywhere. And so it's making me, thank you for that question. It makes me think of, what if it was reversed? You asked about if it's continuous, is it always differentiable? What if it was reversed? Is something that's differentiable always continuous? And that one actually is true. So as long as you can find the derivative, as long as you can find the slope of the tangent line, it actually would be differentiable, which is pretty cool. So again, for those of you just coming in, I wanted to let you know that down in the description below, I actually have the document that you can click on. You can get the link to these problems that I'm doing right now. All right, and last one, number 7. I love a good table problem. I love it. I love like table or graph problems. Like it just makes me think in a different way other than like just being given a function. So let's say j of x and j prime of x are two functions, and we've got a table with a couple function values at x equals 3, at x equals 4. And we've got f of x equals j of x over x squared plus 1. Find f prime. And notice something, it asks us to find f prime, and f prime is not in the table at all, which at first everyone gets a little confused. Like, how can I find this? F of x isn't in the table. Well, it's because we need to first find the derivative of this. And in this video, I think we've done quotient rule twice. So if you need to be reminded of the quotient rule, go back up to some of the previous problems and take a look at that rule that I wrote out. So the first thing, let's write out f prime of x. And I always think it's a good idea to first write out the derivative in terms of x rather than like plugging in the 3 already, because sometimes there could be some different, mistakes that happen. So quotient rule, derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. Derivative of x squared is 2x and derivative of 1 is just 0. So the derivative of the denominator would just be 2x, all divided by the denominator squared. All right, so there is f prime of x. But what this is asking us to find is f prime of 3. So let's find f prime of 3. So what I'm going to do now is I'm going to replace all the x values with the x value of 3 and try some mental math because I'm going to not use a calculator on this. So j prime of 3. Well, you know what? Well, yeah, I'll write it out. And then I'll go back and fill those in. So we've got 3 squared plus 1. And then we have minus j of 3 times 2x. So times 2 times 3. Let's see, that would be 3 squared. Now let's head to the table and let's fill these values in. So j prime of 3, so reading off from the table at an x value of 3, j prime of 3 would be negative 2. So we have negative 2 times, let's see, 3 squared 9 plus 1 is 10. Minus j of 3 is going to be 9. So minus 9 times 6 all over 3 squared 9 plus 1, 10. 10 squared is 100. All right, doing some mental math here, we would have negative 20 minus 9 times 6, 54 over 100, which gives us negative 74 over 100. And I can see they are both even numbers, so I'm definitely going to reduce those. So I would have a negative, what is that, negative 37 over 50, I think, as our answer of f prime of 3 using a table problem. All right, that's it. We got through all 7 problems. So I hope you found that helpful. I think the best way you can get better at calculus is just practicing those rules. In this video, we did power rule, we did quotient rule, we did derivatives of trig functions, we did product rule. Okay, so lots of good rules. You get better at calculus by practicing those rules and also doing as many practice problems as you can do. So thank you for tuning in. Thank you, Cam. Thank you. This is my first YouTube live. That makes me so happy to hear you say that. So I am, fantastic job complaining. Okay, explaining. Thanks for clarifying. I was like, about anything. That is okay. That is okay. But thank you so much for watching. I hope you found this helpful. Again, down in the description below, if you want to click on that link, you can get the problems that we did in this video. You can get that PDF. It's just a free PDF. Just click on that link of all 7 problems. Again, the best thing you can do is just practice your calculus, practice these 7 problems. And I hope in the future, I hope to be, you know what? I'll do this again next weekend. I'll get some practice problems that we can do. So tune in next weekend. I think maybe next weekend I'll do like Saturday. And so tune in Saturday, same time, just next Saturday, and I'll do some more practice problems with you. So again, click on that link below if you want the PDF. And if you're, click that subscribe button, because then you'll be able to see when I do those YouTube lives in the future. I hope to be doing this more often because this was fun. So thanks for joining me, everybody. Great to, well, I wish I could see you, but I'm glad that you're there. And again, I'm Christy, and thanks for tuning in, and hope to see you next weekend. Okay, have a great day, everybody, and I'll see you later. Bye.